everyone. Today I want to share my real experience with Wi-Fi ranging using ESP32 boards. A while ago, I watched some simple videos showing wireless distance measurement with ESP32. It looked very interesting, so I decided to build it myself and test it in a real condition. So in this video, I want to share what I built, how I tested, and what kind of a result I actually got.
First, let me explain very briefly what Wi-Fi ranging is. 802.11 mc/ftm, or fine timing measurement, is an IEEE standard for measuring distance using Wi-Fi signals. The basic idea is simple. One device sends a signal, the other device responds, and from the round-trip time, or RTT, we can estimate the distance between them. Espressif provides an official FTM example for ESP-IDF. If you go to their GitHub page, find FTM and download the example, compile it, and test it yourself. If you are using VSCode ESP-IDF extension, you can simply use the built-in example wizard. Open VS Code and press F1 or Ctrl+Shift+P to open the command palette. Type and select ESP-IDF, show examples, or simply ESP welcome-show examples. A window will open. In the sidebar, look for Wi-Fi and FTM. Click Create Project. Choose a folder on your computer where you want to save the code. Connect your ESP32 into your PC USB port. Select Options in the bottom of the VS Code. Choose UART for serial. Select target chip type such as ESP32C3. Select SDK menu configuration. It will take some time to show up the menu. In the menu configuration, make sure FTM compile option is selected. Then you are ready to build and flash the code. Using that example, you can run one ESP32 as an initiator and another one as a responder. When they communicate, you can receive RTT measurement results with very fine timing values. I started from that example and gradually added sophistication. In order to compare and collect test data, I modified the code so that I could collect multiple initiators data at once. Now, let me show you the outdoor experiment. In this test, I used 5 initiators connected to my notebook and 1 standalone responder. For initiator, I programmed 2 ESP32C3 DevKit-M1 boards, 2 Heltec ESP32 S3 wireless tracker boards, and 1 Xiao ESP32 C6. I placed them side by side, and from a laptop, I measured the RTT latency one at a time. For the responder, I used a Xiao ESP32 C6 board with an external antenna. Then I moved the responder from 1 meter up to 20 meters. I also tried longer distance, but beyond around 20 meters, the signal became much weaker and reliable measurement was difficult. So for this experiment, I mainly focused on the testing the range from 1 meter to 20 meters. Now let's look at the data. After collecting the outdoor measurements, I analyzed the data and plotted several graphs. The first graph to see is the measured RTT of all ESP32. Each line in the graph represents a different ESP32 board. As you can see, we can clearly see pattern increased and decreased RTT value by the distance, or measurement event. The measurements are noisy, and different boards behave differently. The error is definitely not small, but even with that noise, we can still see a general trend. RTT changes as distance changes. Next, I fitted the measured RTT values to distance using a least squares method. This part was quite interesting. For several boards, even though the absolute error was large, the slope was fairly consistent once the initial bias was calibrated. In other words, if the starting offset is adjusted properly, the measured RTT still follows distance in a fairly stable way. That means the system may still be useful, even if it is not as perfect as the theory sounds.
Another surprising point is the oscillator quality. When I checked several ESP32 products, I found that their oscillators are usually only around 1 ppm to 10 ppm in accuracy. But in a wireless ranging field, many people believe that if you want sub-meter or even centimeter level accuracy, you usually need a much better oscillators, often in the ppb level class. So it was quite surprising that these low-cost ESP32 boards could still produce this level of ranging performance.
Based on these experiments, I also made a very simple handheld Wi-Fi distance meter with only an OLED display. Now let's go back outside and test it. As we discussed earlier, I first apply the initial calibration, and then I move the device while measuring distance. As you can see, the displayed value is not exactly perfect, but it is roughly in line with the tape measure.
So my conclusion is this. ESP32 Wi-Fi ranging is promising, but real performance is very different from what a simple theory may suggest. Still, for a low-cost experimental platform, I think it is surprisingly powerful and worth exploring. In the next video, I'd like to show some more interesting applications that can be built using Wi-Fi distance measurement.